Hello everyone. Today we are going to cover some examples on relational algebra expressions. So for this lecture, we will be following this particular example which is given in your textbook also. So here in this schema you have four tables. One is product, then the PC, then laptop, then printer, and in product you have attributes such as maker, model, and type. And the type of product can either be PC, laptop, or printer, right? And over here in the printer, the type can either be laser or inkjet. So the key thing to note over here is that in all these slides which I'm going to cover today, the model number is unique. So that means no PC, the model number, let's say it is some 1 to alpha B or something like that. So that model number, if it is for a PC, then laptop or printer will not have the same model number. In other words, a model number is unique across all the three types of equipment that we have here. Okay, so that is the primary assumption that we are making, that a PC, laptop, or a printer cannot have the same model number. Okay, with that assumption, let's go forward. Okay, so first we will have some simple expressions, and then as we go forward we'll cover more and more complicated ones. So the first query that we are interested in is to determine the PC models. The first query: what PC models have a speed of at least 3 gigahertz? Okay, so for in these slides, I'm going to write the expression by breaking it up into a couple of smaller expressions so that you can easily understand. Okay. So for this particular query, what PC models have a speed of at least 3 gigahertz? So you have to, whenever you get a query like this, the first question that you have to ask is which table will you get your information from, right? So here we want models and we are interested in looking at the speed. So both this information happens to be in this PC relation, right? So now the way we are going to formulate this query is that first I'll take an instance of the PC relation and I'll pass it through my selection operator where I'm putting a selection condition on the speed attribute, and I want the speed to be at least 3 gigahertz. So after my PC table passes through this selection condition, I'm creating a sort of a temporary relation. In that temporary relation, I have all the tuples from the PC relation where the speed was greater than 3 gigahertz, right? So that is the intermediate relation. And finally, from that intermediate relation, what I am interested is to actually project out, right? So we want to have only the model information. Recall that after I perform the select operation, the schema of R1 is same as schema of PC. It's just that R1 will have slightly fewer tuples than this PC because we are performing an filtering operation. So on this R1, I'm going to perform my project operator, and in this particular query, I'm interested only in the model numbers. So I'll pass R1 through my pi, which is the project operator, and then I'm going to take out only the model column, right? And and then the resulting R2 will be your final answer. Recall that this kind of breaking is only for our understanding. In fact, all the expressions which I'm going to cover in this particular module, you should see that in terms of which is easier to understand. Do not think about performance here. In fact, at relational algebra expression level, we don't even consider about efficiency, because this is all trying to represent our business requirement using some set of relational algebra expressions. When we come to the physical model of database, then we'll actually think about the performance and efficiency of the queries that we are writing, right? So here, what I meant to say was that instead of breaking this query into two parts, instead of writing R1 here and here, what I could have done is that I could have simply taken PC, and I pass it through this select operator, and then put a bracket over here, and then pass it through my project operator, right? So this kind of nesting can be done of operators, right? So hope this query is clear. Let's move on to the second one. Okay, so the second query is, which makers have a laptop of at least 100 GB hard drive, right? So here, the first thing that we ask is that, what information does the query need? So in this particular query, I'm interested in laptops with a specific hard drive capacity, and I am also interested in the makers, who is the manufacturer of that particular laptop. So clearly, all of this information is not in one table, it is in two tables. And to be precise, our two tables of interest would be the laptop table and the product table, because the maker information is in the product table. So what we do is that, we perform a join between laptop and product, and we would be joining on the attribute model. You can do, natural join here, or you can do theta join, or so here what I have done is that I first created a cross product, a Cartesian product between my product table and laptop, right? And then, I'm storing it in an intermediate relation called as R1, and on that R1 I am applying an select operator, right? So in that select operator, I have written my join condition, which is product dot model is equal to laptop model, and I am clubbing the another select condition of that, the hard drive should be at least 100 GB. So I have clubbed that condition along with this. Recall that, in the selection, in the select operator, I can have any Boolean value expression, right? So I can have here and all of that, you can do it, right? So as I always say, the way this is executed is that, I am going to pass through every tuple in this temporary relation R1, and for each of those for each of those tuples, I am going to check the following two conditions. The first, I'm going to check if the product dot model was equal to laptop model or not, and if that is true, I'll check the second select operation, right? And the tuples in R1 which pass through this select operator will be stored into my temporary relation R2, right? So this is an example of a join query. And as I kept on saying, right, you can solve this query in multiple ways. You could have done a natural join also, a theta join also. For sake of illustrating, I'm doing it via Cartesian product followed by select operator. Okay. So now after doing this too, we'll have all our tuples of interest in R2. But note that, we are interested only in the makers, right? So finally, we have to perform an project operator on R2 and then just take out the maker. So this is a general philosophy that you should follow. The project operators are always put at the end. So always the way you have to think is that, you have to first start with the tables. What tables do you need? Do you need to perform a join? If you need to perform a join, what is the join condition? And after that join condition, what select operators you have to put? Things like hard drive at least 100 GB or RAM at least 64 GB, something like that, right? And after you are done with all of these things, then you actually go with the requirements of your project operator, right? So do not start thinking from the project operator first. You will not get a appropriate answer. Okay. So and just similar to what I have taught in the earlier lecture, whenever in case of any doubt, for queries like this, if you have any doubt on how this is going to work, always create some small examples. So create a small product relation on your paper, put two or three tuples, put some tuples in the laptop also, you just work it on paper, create a cross product. You know how a cross product is done, and after that cross product is done, simply just go through each tuple of that cross product, and then you check this select operation, and then you can convince yourself that this query really works. And in the beginning, I know it may be bit of a jump, but I think slowly you'll get hang of it. So the practice is key here. Okay, so let's see what. Okay, so this is a slightly complicated query. So let's break it down slowly. So here, what we are interested in is we want all those manufacturers which sell laptops, but they do not sell PCs. Okay, and how are we going to do this? So you may recall our set difference operator. So let's say that if I had given you the list of all the makers who sell laptops, right? Let's say that set is given to you, and then you have another set B, which contains the list of all the manufacturers who sell PCs. Now, in our relational algebra, we have the set difference operator, and if I take the difference between these two sets, what will I get? I will get all the manufacturers who sell laptops but not PCs. Remember that when I get the list of all the manufacturers who sell laptops, in that list I may have some manufacturers who are selling PCs as well, but we want to throw them out, right? So if I just do this part, uh, select from product on the condition that type is equal to laptop, right? So you'll get all the tuples where the laptop is the primary thing, but there can be a manufacturer who sells both. Now, if you have to take out only the manufacturers of the laptops, you have to use the set difference operator. Let me show you that. Yeah, okay. So this is what it is. So first I take product relation, I pass it through my select operator, and my selection condition is that the type attribute should be laptop. So that means I'm going to loop over all the tuples of product, and whenever the type is equal to laptop, I'm sort of filtering out those tuples into R1. And then similarly, I take another instance of product, and then again I loop over all the tuples of product, and then I filter out all the tuples where type is equal to PC, and then I'll store it in, let's say, R2, right? So now I project R1 by taking out all the makers, and similarly I project R2 by taking out all the makers, right? So here what is happening is that when I am passing this R1 through my project operator, and I am projecting on the maker column, what I'll get is that I'll get a list of all the manufacturers who manufacture laptop. They may manufacture printer, PC, everything else, but they certainly are manufacturing laptop, right? And then similarly, when I see this part, pi maker over R2, I will get the list of all the manufacturers who are making PCs, right? Now, if there is a manufacturer who is neither constructing laptops nor constructing PCs, then he that particular manufacturer will not be there in either R3 or R4. Those are clearly out, right? Now, there can be some manufacturers who are making PCs and, let's say, printers, so that guy will be here. And over here, you can similarly have manufacturers who are making laptops and printers also, right? And if there is a manufacturer who is manufacturing both laptop and PC, that particular company will show up in both the lists, right? Now, if I am doing R3 minus R4, We call that, what is this set difference operator? In set difference operator, when I do this, the output will contain all the tuples of R3 which are not there in R4. And now what will be those tuples? Those are the manufacturers who sell laptops and maybe printers also, but they are certainly not manufacturing PCs, right? So that is how this set difference operator is working out, right? So of course, you don't take my word for it. For each and every expression that I'm writing in the slides, so you should go through them, work it out. If you feel that things are not clear, we'll have a session during that live session on those days, and then you are more than welcome to ask questions on how these things are working, right? So don't take my word for it. Do not try to mug up this, right? You will end up badly. So in the exams, I can give you any query like this, and you need to catch the fundamental understanding of how these operators are working. Otherwise, you will be in big trouble, right? So do not take anything for granted. Question every expression which I am writing here. Sort of, verify it why this is true. And if you think that there is some error, you please get back to me. Okay. Next expression. Okay, so I think this is a slightly more complicated expression, and we'll try to go slowly. Okay, so the query that we have here is that we are interested in determining model number and price of all the products that are made by Dell, right? And Dell can make a PC, laptop, printer, it can be manufacturing several of those, right? And for each product type, it can have several model also, right? So if you want to do this, uh, so the way this query is formulated is that first we are going to get all the model numbers and price of, let's say, laptops, and then I'll get all the model numbers and price of PC. Then I'll get all the model numbers and price of printers. Then I can do an set union across these three relations to get our final answer, right? And now let's pick one case over here. Let's say I'm interested in just finding the model number and price of all the laptops which are made by Dell, right? So how I'm going to do it? First, I'm going to pick the product table, pass it through a select operator, and I'll put the condition as maker equal to Dell, right? So after I do this, I will get all the models over here, all the tuples from here, where the manufacturer, the maker is Dell, right? So now if I wanted to get the model number and price of the laptops, the way I'm going to work is that, I'll take R1, okay, and then I'll join with laptop. And recall that the model numbers are unique across all the three, right? Because a laptop will not have the same model number as PC, and vice versa, so on. So now if you join our R1 with laptop, right, on this model number attribute, you are going to get all the tuples, all the laptops which were made by Dell, right? And that's what this is. So I'll so instead of join, the way the query is written over here is that, I took an instance of laptop, did a cross product with R1, and then followed by a select operator on the laptop dot model is equal to R1 dot model. So now R3 contains all the laptop models which were made by Dell. And for these models, I am interested in determining the price and, of course, the model number. Now, how would I do that? I'm going to take this relation R3 and pass it through my projection operation. In the projection operation, I am going to project out the columns of model number and price. right? I don't need other details like RAM, hard drive, screen, and all that. I'm interested only in the price of the laptop and the model number, right? So I take R3, I pass it through my projection operator, and then I project out the model number and the price. The same thing is being done for the printers and the PCs as well. So at the end of this initial phase, I have R5, R6, and R7. R5 has list of all models and prices of laptops made by Dell, and then R6 has all the model numbers and prices of the PCs, and similarly R7 has the prices and information about the printers, right? And recall, and you may notice that the schema of R5, R6, and R7, it's the same. They both have two columns. One column is the model and the second column is the price, right? So I'm allowed to perform an union operation among all these three relations, right? Because as you remember that, before performing a union operation, the schema should be identical across the participating relations. Otherwise, it's not allowed. So here, I can perform the union of R5, R6, and R7. Let's say, okay, I'll have to change this to maybe R9, right? Okay, and over here, R9 will contain my final set or final relation, and in that set I'll have the model numbers and prices of all the products. That means, either PC, laptop, or printer which were made by Dell. Okay. Okay, next question. So here we are interested in finding pairs of PC models that have same speed and RAM. Okay, pairs of PC models. So that means, two PC models who have exactly the same value of the processor speed and RAM, right? Now, how are we going to get this? So there is an, I purposefully put this question here. Uh, so whenever you have things like this, pairs of PCs or triples of PCs and all that, right? So this is hinting back at our notion of self join, right? So let's take two instances of my PC table, right? So whenever I'm using two instances of PC, or for that matter any relation, I put these numbers 1 and 2 to disambiguate. Ideally, we should have used that rename operator and all that, but that's okay, as long as we can quickly understand and we are not making any mathematical error, it's fine, right? So we'll follow this terminology that, if I want two copies of PCs, I'm going to write PC1 and PC2, right? Without going into too much nitty gritty of that rename operator and all that, right? So here I have two copies of the PC table, PC1 and PC2. I have conducted an Cartesian product. So basically, if I have let's say 10 PC models, then after this Cartesian product, so 10 paired up with itself, again 10, so you have 100 pairs, right? So this is the result of the Cartesian product. Now out of this 100 tuples, I'm going to parse through each tuple, and then I'm going to check if the PC1 dot model is not equal to PC2 dot model. So remember that, in PC relation, the model number is likely to be an candidate key. At least in this example, it's an candidate key. So that means, no two tuples in the PC table will have the same model number, right? So now let's pick any one particular tuple over there, right? It will have a model number, and it is going to be matched against 10 other tuples from the second copy of PC. So out of these 10 tuples, which would be created by joining the first tuple of PC, 9 of them would pass through this select operation, because our model number is an candidate key. So that means the first tuple of the first copy PC1, let's say, if it has the model number 100, then in the second copy, this tuple with the having the model number 100 will not match with the tuple with basically the same tuple having the model 100, but it will match with all the other 9 tuples which are there in your second copy of PC, right? So you can actually make a very educated guess on how many tuples you will have in this R1, right? So basically, let's say in our example, we had 10 tuples in PC1, and from our logic, we know that each tuple is going to match with exactly 9 tuples after this, right? Because model is your candidate key, right? So therefore, the number of tuples in R1 is actually going to be 90, right? So what we have done is that in R1, now I have pairs of PC models, right? So each model, each PC is being paired with a different PC, which has a different model number, right? So by constructing this R1, I have taken care of this part. Pairs of PC models I have constructed and put it in R1. Now what we want to do is we want to select only those pairs of PC models that have identical values of speed and RAM as well, right? So now in order to get those, what I'm going to do, I'm going to loop over my R1 and I'm going to perform an select operation here saying that, PC1 dot speed should be equal to PC2 dot speed, and similarly PC1 dot RAM should also be equal to PC2 dot RAM, right? So whenever that also is satisfied, then I put it in my temporary relation R2, and then finally on R2 I perform the project operation, right? So the key thing that you have to remember is this part. Whenever you have to take whenever you have to consider things like pairs, you must always do a self join. And in that self join, a condition like this, PC1 dot model not equal to PC2 dot model, then you will be creating pairs where the items are different, right? And after you created this, you pass it through whatever condition you may want. You may say that, for example, if my query was select all those pairs of PCs where they have the same speed, but one is $100 more than the other one, right? In order to do that, again your R1 will be same, but in R2 you will have this PC part, but for price maybe you will have something else, right? So things like that. So all those things can be done, right? So but the primary concept is that whenever you have to get the pairs, you have to do a self join. If you have to get triples, you have to do 3 times cross product. Okay. We'll have examples of those also. Okay. Forward. Yeah. Okay.